So previously in the earlier lecture, we have talked about how to use the neural network to do feed forward and to uh, make the prediction. When you have the parameters ready, then you are able to use those weight and bias to make a good choice. But now, what the question is, how to find these good parameters, good W and good B. And the answer is the gradient descent. So I want to briefly revisit the gradient descent concept we mentioned before. Okay, so actually when we are talking about the linear regression and the polynomial regression, we mentioned about this. Because some of the optimization problem, there is just no way, no good way to find the solution. So it is also nice to have some approximation to find the minimum or find the maximum. So the setting is usually like this. There is a target function. And in fact, most of people call that as the cost function. You want to decrease, you want to drop the cost. And we also see that it is called loss function in neural network. Okay, but they all refer to the same thing. We want to minimize a certain value. And so this function, I just briefly call that as f, and usually it takes several variables, and then it generates a real number. And for convenience, I just call these variables as x vector. And sometimes it has just way a lot of variables, and here is just for brevity that I make it simpler. Now the goal is to minimize f. And let's recall what are the steps. So the first step is to pick the x, this quantity, these parameters randomly. And secondly, you have to calculate the gradient of f over x. Okay, and let's refresh our mind about this notation. This is a direction, it is a vector. It is point to the direction along which let me say that again. Directions by increasing, say that again, by moving x along this direction, f will increase. Okay, so if you kind of have the valley here, and you are standing here, then you know going to this direction will increase. So this is we call that as the gradient of f. So each x will give you a gradient. But actually, calculating this gradient can be tedious. It is not just for like for you. I mean, actually, for many people with mathematical training for several years, and it is not so easy to calculate this gradient, particularly when the function is hard, is complicated, just like the neural network. But anyway, you either find the gradient or either you calculate the gradient by yourself or find the gradient. Okay, there's no much difference, but the difference is that find the gradient means that you can just ask somebody, find the textbook and find the solution, and just find the gradient. Okay. Uh, okay. The third one is saying if we have the vector x, then we should replace x with x minus alpha times this gradient. And this alpha is a positive number, and it is called the learning rate. Okay, so like what I said, this direction, going along with this direction will increase the function value. But we want to decrease the function value, so we are going to go to the opposite direction. But we might not want to go too far. It will maybe jump from this side to the other side. Okay, we want to go down a little bit only. And so this learning rate is a small number, usually 0.1 or 1, and it will allow you to update the location. So keep repeating this process, then it will allow you to drop the function. So let's move on to the second handout. This handout is called Neural Network number 1. Neural Network number 1. This handout actually is quite comprehensive, but I want the simple version for you to digest. So I create another one. But the beginning of this handout is fine. It is talking about the gradient descent. Okay, so this picture is much better than I drew before. Imagine that this is the map, and the map will have some contour or some curve to indicate that everything on this curve has the same height. And so you can imagine that this is kind of the valley of the whole thing is a valley. So when you standing at the point of x0, then you can calculate the gradient. The gradient will tell you, okay, going to this direction will increase the function. So gradient descent tells you that go to the opposite of the gradient. And when the next step you standing on x1, then gradient will tells you that it is the opposite side here, and then you go to the opposite of the gradient, then you will move on. So it will keep directing you to the bottom of this the center, the bottom of the valley, and that's the idea of the gradient descent. So here has some code that if you want to play with, I will briefly mention what it is, but you have the code, you can play with it. So I defined a function called gradient descent, and this is doing the gradient descent for a function. Okay, and this function you have to supply its gradient, and that's the hard part sometimes. And you also have to tell me what is the dimension, how many variables are in these functions. And if you want to set up the number, the initial point, then you can try to set it up, and you can set up the alpha. If you did not set up the initial number, then I will randomly pick a random a vector, and try to keep recording what are my location. So initially my location is this random position. It is just no information, it's just a random number. And then starting from the step 1, step 2, keep going, then I will keep applying this formula. Okay, so no matter what the gradient it is, you have to tell me what is the gradient. And so I will calculate the gradient of this point and update what is x. x equal to x minus alpha gradient and record the same thing. So that's the gradient descent. Let's try to look at some simple example. The function f is x squared. X squared, if you take the gradient, it is equal to 2x. This is just mathematics. You can do that, or just try to find the solution. Now, the gradient descent. Ideally, this is the parabola, which is with the center at the 0. It's a parabola with the minimum at the 0. So ideally, no matter where I start, it will gradually move to 0. So let's try to do this a little bit. F is equal to x go to x squared, and gradient f is x go to 2x. Okay, the formula I have x is the array, but it doesn't matter. Just try to make it work. Okay, so if you apply the gradient descent and then you do the dimension equal to 1, and then let's see how it would look like. So randomly, the x was chosen as the minus 0.2. Minus 0.2. And if I use alpha equal to 0.1, then it will keep going to the right, going to the right, going to the right. And eventually you will go to very close to 0. And if you want, you can make step higher. Then eventually you will go to very close to 0, like e to the minus 10 power. Okay, but then you can try to use something else. Alpha is the learning rate. Learning rate will determine how fast you are learning. But if you try to use something too large, alpha equal to 10, you just go one step, but this step goes from the left bank to the right bank and keep going higher. And so in this case, you will see that this is plus 11. You see, just within a few steps, you will go from very close to 0 to 17 and minus something and 6,000 and keep going on. And it's easier to get a mistake. So when the learning rate is too large, it will cause some mistake. It will not converge. Then you can still use 1. I was using 0.1, right? But if you use 1, then it's still terrible. You see it is 1 minus 1 minus 1 minus 1, 1 minus 1 alternating in between. This is not a coincidence. For this particular function, if you go one step, then it's exactly like this. And there are some miracles if you choose 0.5. If you choose 0.5, no matter where you start, it will immediately go to 0. But this is just by luck. It's because this function is too easy. You see 0.5 and this 2 will combine to be 1, right? So which means you will do alpha gradient, which is just x. And so minus x will go to 0. And so this is just by luck. And usually you will try this alpha to see, okay, sometimes it is too large, it does not converge. And if you choose 0.1, then you will see that, okay, this is dropping too slow. And then you can increase the rate a bit faster. Okay, so that's something for you to play with. And now, the handout is there, so I want to finish the last theoretical part and leave the code and leave the time for you. So now we have a basic understanding of the gradient descent, and now I am going to tell you how to train the neural network. So let's briefly have an like a review of what we talked about previously. Let's say we have a collection of data. It is m by d as usual, and each of the data set we call it as xi. And in the end, we have the answer y. And this answer y, the dimension is not sure. It depends on what kind of things you want to train. But in the end, you still have n answers. We call that as yi. So what we did before is take one of the things and take it as the input as a0. We take one number and then one data point and then input that as a0. And although we have the beautiful and complicated neural network picture, but actually what it did is just transforming a0 to z1 and apply the activation function to make it into a1. And after that, use a1 to generate z2 and apply that with the activation function a2. And you will keep doing this until it goes to the end, which is zl, and apply the activation function al. So this direction is called feed forward. Feed forward. And our goal is try to make this al very close to yi. Okay, so goal, we hope when you take one data, AI, and then you plug in, keep going until you reach to the end, which is AL. So AL is actually a function of xi. You take a data and generate that until to the end, which is AL. And then I hope that it's very close to yi. Okay, that's the hope. Now, in order to do this, let's define the loss function. Okay, this C function is taking the difference between them. And because both of them are the vector, I'm going to take the difference between them and take the square and take the sum. This is the norm of the vector, and I take the square. Somehow, usually, there is a coefficient here. It is easier when you are doing the derivative. If here is x squared, then this square will come down, and 2 and 1 over 2 will cancel. But this is just a coefficient. Now, you see, this is just the error of one data. You pick one data and go to the end, calculate the error. And so, actually, we have a lot of data. We want all the data go to the right-hand side, and we calculate all the errors. So we want to take the sum of all these errors. And we want to take the average of that. Otherwise, if you have n equal to, say, 3 million, then this quantity will cause some overflow. Theoretically, mathematical does not cause any error, but if you don't divide it by this n, then you will cause some overflow on your computing process. So we call this as the loss function or cost function. Okay, now let's try to think clearly about what's going on here. We have a set of data and a set of answer, and somehow there's something more here. Each step we have W1, B1, a matrix and a vector. And actually we have several matrices and several vectors. All right. So this C depends on X and Y, and also all these weight matrices and all the bias vectors. But however, we are going to fix these two, right? When we are training the data, we are training the model, we have the data ready. We are not going to change the data anymore. We have X and Y ready, and we are trying to train W and B's so that the cost function is minimized. So the whole thing, the main idea of a neural network, aside from this structure, the main idea of training a neural network is applying the gradient descent. To the cost function. Okay, we want to minimize it, and our details is to adjust these W's and the B's so that the loss function is minimized. So actually, it is not too bad. The whole thing is a structure of neural network. And second thing is you have to understand the feed forward. And the only things you need to know about the training is you have to apply the gradient descent to these parameters. And the computation is tedious, as I promised. So I'll just give you the formula. Okay. And this process is called the backpropagation. And the reason is it is doing the opposite way. So let me show you how does that look like. Okay, and in the end, we will have ZL, and AL. And we wish that to be very close to the Y data. So let's look at the relations between all the things. Okay, we have the cost function. This cost function is generated by AL and Y. Okay, but Y is fixed. So basically C is determined by this AL. And what we want to know is this C function, if I change AL a little bit, how much will C change? Okay, so this is the first gradient we can calculate, although that's not what we really need. And then after, before this sigmoid function, we can also come back, right? It is this ZL to generate AL. So we can use ZL to determine how much to change in C. So we will have gradient ZL and C. So again, if we look at this notation, it means ZL has to go to this direction in order to increase the value of C. This is a vector, it is a direction. And the reason we call that as the backpropagation is because there is a formula allowing you to generate this gradient for each of the L, each of the Z. Okay, and I will tell you the formula later. But still, remember that we are using the W1, B1, and W2, B2. And what we really want is not the gradient of Z. What we really want is the gradient with respect to W and B. So, with this at hand, with the gradient of Z at hand, there is some formula allowing us to generate the gradient of W1 for C and the gradient of B1 for C, and for each of them, I'm able to generate this one. Okay, so that's all we want, really, because this Z function depends on AL, and AL depends on ZL. ZL depends on these parameters. So we will use this to generate all the gradients along with that. And then ZL depends on ZL minus 1, and so we are able to calculate the gradient. And ZL minus 2, Z2, Z1. And Z2 depends on the W and B. Z1 also depends on the corresponding W and B. So what we really need is this part. And this is the gradient that we want. And with this gradient, this W have the same size as W, and we will do the gradient descent on this W. We will do the gradient descent, use this gradient to this B. So use these gradient to update all these parameters. So it can somehow complicated, but after a while you will get used to the idea. And the main point is really just a gradient descent with a certain complicated formula. So here are the formulas. Backpropagation rules. It is really a bit complicated. Okay, so C, if I want to calculate ZL, that's the first one I mentioned here. This one, you have to calculate C over AL. And then you have to pass through this sigmoid function. So we will do the chain rule and sigma prime and ZL. Okay, and here has some notations. The first one is this one. This is the entry-wise product. So this is a vector of size AL, and this is also a vector of size AL. Then you will do the entry-wise product between these two. And NumPy is very good at this, so this is not a problem. But somehow, what is this? We have to start with this one, right? And so this is on the left-hand side is the general backpropagation rule for any C and any sigma. But now, if C is, well, let's say for our C and the sigma, we can customize the formula into the following way. The gradient of C over AL is not too bad. It is just equal to AL minus YI. Okay, and the other thing is the sigmoid function. This is simply the derivative, and so you take the derivative or find the formula or ask the computer to do so, you will see this formula. It's just some computation. So with this formula, you are able to calculate the AL, gradient of AL, which is just the difference between AL and YI. And with this gradient of AL, and you can calculate what is the gradient of ZL. Now the second formula tells you how to use ZL to determine the gradient of ZL minus 1 and ZL minus 2. So if we are interested in zi, a certain layer, the gradient of a certain layer, then we can use the give me a second. Okay, we can use the gradient of the next layer, zi plus 1, and that's multiplied by the W matrix. So you see ZL and ZL minus 1, there is a W matrix in between. This is the W matrix we want. So we use the Wi plus 1 matrix multiplied by this vector, and the whole things, once we are done, we have to pass through the sigmoid function again. Okay, these are the most complicated part, but we're almost done. Then we have to know, let me write it here as a revisit. Each of the zi is equal to the previous a minus 1. You do transpose, multiply by wi plus bi. Okay, so now we have this zi already. We want to use zi to find out the corresponding things for b, corresponding gradient for w. If you do the gradient here, it's basically like a derivative of x is equal to 1, so it is the same. So gradient of bi is exactly equal to the gradient of z. Right? If you change this a little bit, z will also change a little bit, so it is the same. And applying the chain rule, you will get the things. And w is a little bit different. If you do w, you move the w a little bit, you will change this quantity to z, right? So it is actually the product of z and a. All of these require some careful mathematics computation, but I'm just telling you the intuition. You do the ai minus 1 and do the transpose. So actually here is a column vector, here is a row vector. After you multiply that, this is a matrix. Okay, so I will leave this, I will upload this page very soon, but I still have a little bit time, so I want to show you the code in the last example. And I want to say that it is not too bad, okay? So give me maybe last 5 minutes of attention, and we are all done for this semester, and I just want to show you how to code the neural network by yourself. Okay, so neural network, small example. This is the last Jupyter handout that I'm providing. Okay, so you import some metrics and then do something and kind of ignore everything here. The only things I do here is the one-hot encoding. So I prepare what is X and I prepare what is Y, and this is the way to do one-hot encoding in a different way. So anyway, X and Y is our data. So I'm going to scroll down because those are not important. Don't look at that. Now, define the sigmoid function, and the d sigmoid is the derivative. So this is just simply calculating the sigmoid function and the sigmoid function derivative. Now, this is the whole part of neural network. Not too long, right? Compared to, say, decision tree and something else, it is not too bad. I decided to generate a neural network, which is again 4 neurons, and 3 neurons. In total, there are 3 layers. So there are 2 sets of parameters in between, and those are what we want to train. Okay, so let's generate these parameters. This is the first step of gradient descent. So those are random numbers. Every time, if you are lucky, then you are very close to the answer. If you are unlucky, no worries. Gradient descent will help you to direct you to the answer. Now, we have the learning rate. Let's say alpha equal to 0.1, and n is just recording what is the number of samples. Now let's ignore this for loops a little bit and make it smaller. Now, forget about the for loop, okay? The for loop does nothing. You just run these part of code several times. Okay, so we need to do feed forward, and we have seen that before, so kind of forget about that. But the thing is that for this part, I'm not going to do each data point one by one. You see that I'm doing the NumPy, I do every data point together. A0 is not just one point, it's actually all the data point. And Z1 is the Z1 of all the data point. So you see, Z1 is supposed to be a vector of 4, length 4, but now it is n vector and each vector is length 4. A1 is n vector and it is a 4 vector. And Z1 and Z2 and A2. So in the end, you get n numbers. N samples give you n numbers, n vectors, and it is n numbers of in 3 dimensions. Now you can generate the cost function and try to ignore this part first. Okay, so you can generate the cost function by yourself, and you see that it is A2, the last A, the output and Y, take the difference and then take the square, take the sum, and divide it by 2, divided by n. So this is the cost function. So let's change accuracy to 0 and ignore these 2 parts first. Now, the next thing is the backpropagation. Although the formula looks complicated, and actually this is not quite easy, I would say. So, but the whole thing is implement the formula we had before, and you see we calculated dz2, dz1, dw2, db2, and so on. Each of the d is the gradient of each of them. And again, for example, this db1 is the gradient of all the sample. You have n samples, and then each sample will give you a gradient. So it will give you something like this. And you have to find some time to realize what it is, but this is basically calculating the gradient. And in the end, you also understand this formula. It is x is equal to x minus learning rate multiplied by the gradient, the opposite direction of the gradient. And as I mentioned, for example, we used B2 as the example previously. B2 is a collection of gradient, and in order to do the real gradient, the gradient of the whole data, you take the average of the gradient. It's actually also caused by this 1 over n. Your cost function is the average of all the data. So your gradient is also the average of all the data. So if you run this code for several times, then at least, forget about accuracy. Okay, at least this cost function should drop. And if you see the cost function is dropping, then that's great. It is at least on the good direction. Now you can try to calculate the accuracy by yourself. Again, A2, the argmax is the real answer, and so maybe you want to know what is the prediction, how many prediction is equal to the answer Y, and you can calculate the accuracy. So if you do this, and print the accuracy all the time, then you will see the accuracy is 0.3, which is very bad. But if you keep training for this one, actually let me try to change that to 1000 and try to run that a few more times. Then you will drop going up to going up to this. But 0.6 is not quite well as well, right? That's the drawback of neural network. There are several ways to improve the neural network, but because this is a very primitive neural network, so it does not go well. At least one thing you can do is to normalize the data without updating the neural network. One thing you can do is update the data. Because you see the data is actually quite big, so that means that if you are doing a gradient descent, it might goes too far. It has to go too many steps. So one thing you can do is to shift the mean to the origin and also divide it by the standard deviation to standardize or normalize the data. And if you do this, and you will see that this time is not too bad. I restart the parameters, but it's quite fast that you run several times, it will go up to 90 some percent. So a full project of machine learning or data science is composed of a good model, good choice of parameters, good way of training the model, and also feature engineering. And in that way, you are able to do the whole machine learning.